Good evening, everyone. Welcome to the session here, which is the sixth session that we are holding from the time we have started. I'm going to just share with you my video face, just in case you don't know me. And if you ever see me on the street, tell me, Prof, I was in your class. So I would be very happy to shake hands with you and say hello. Okay, we are still getting people coming in, although it's 4 minutes past 5, but we are going to start nonetheless. All right. So today we are going to do a lot of questions which relate to what we call progressions or sequences. Now, I don't know how many of you have been accustomed to sequences or have been exposed to them. So I'm going to give a quick rundown into what these things are all about. All right. So let's say a few things about sequences. Now, a sequence is just a collection of numbers and normally we just separate them by commas. So you have, and usually there is some kind of a rule which tells you what the next one is. Like, for instance, you're going to have 4, 5, 6, 7, and so on. You can go on like that with no ending, or you can go 4, 5, 6, 7. You can go right up to, say, 236. We put dot, dot, dot like this to illustrate that there are lots of other numbers, and this pattern continues. Okay? Now, these are all consecutive numbers, but they need not be like that. You could have had 18, 22, 26, 30, and so on. And you can see the rule here is you keep adding 4. But the rule is prescribed. Normally, we are told what the rule is, right? And so you will know what the sequence is. Sometimes you can even have a backward sequence. Like if you wrote it down like this, 30, 26, 22, 18. So this is what you call a decreasing sequence. It's getting lower and lower, all right? Now, the kind of sequences that we are going to consider are these types. 47, 42, 37, 32. So these sequences which I've listed here, they've got a common property. Namely, now listen carefully, each term, you call these terms. This is the first term, second term, third term, fourth term, and so on. So each term is occupying a certain position, first, second, third, fourth. So just understand that the terms occupy certain positions. Like this one here, 14 is occupying the fifth position. So each term is obtained from the previous one by adding or subtracting a certain number. So here you can see I keep adding 1 to get to the next one. Here I keep adding 4. Here now I'm subtracting 4. 30, 26, 22. I'm subtracting 4. And here too I'm subtracting 5. But we normally say, we don't say subtracting 4, we say adding -4, which is the same thing. And here we are adding -5. Okay, so in a sequence like this, you have the terms, and we write down T for term, and we put a small number at the bottom, for instance, make it 3. This is a symbol which says the third term. So in this sequence here, T3 is equal to 6. Same here. So in here, T3 is 26. Here, T3 is 22. And T3 is 37 here, right? That subscript, what you call a subscript, refers to the term, the position of the term, right? So this is the third term. See, so in general, you have Tn, where now n can be anything. It could be 3 or 4 or 5. It could be even 1. If you're talking about T1, it means the first term, right? Normally, for the first term, we use a symbol A. Just remember that. The symbol A is usually used for the first term, but for the others, we use these symbols here. Okay? So this is the third term, this one here. This is the nth term. So you got these symbols here stand for terms. Now over and above that, there is this number which you're adding and subtracting. But I said we are adding them. That symbol is D. D actually stands for difference, because you take any particular number and you subtract from it the one just before that to get you the difference. So 6 minus 5 is 1. So that is what we are doing here. We're adding 1 all the time. Like here, 26 minus 22 is 4. That's the difference. So we are adding 4 all the time. Here you've got 32 minus 37 is negative 5, right? And that is your difference, the D, in this example here. So D is actually called the common difference because it's the same difference right throughout. I said these things the sequences we are working with, they all have this pattern that you are adding something, the same thing right throughout, or subtracting it. Okay. So with that quick introduction, I just want to tell you a couple of things. So in general, if we don't say what the first term is, we call it A. As I told you, the first term we usually is A, and the difference is D. That means you're adding D to get the next term. Of course, if D was negative, you'll still put A plus D, but the D is a negative number. Right? So you'll be subtracting. The next one, you keep adding this. So you get A plus 2D, A plus 3D, because you add the same thing, right? Now, you can see here that this is the second term. This is T2. This is the third term. This is the fourth term. Now there's a pattern here. You can see it's all of them have got A and D in it, but the number in front, 3 here, is for the fourth term. 2 is for the third term. And 1 is for the second term. So if I know what the nth term is, then it will be the same pattern, A plus, but now the coefficient of D is 1 less than the subscript. So it's n minus 1 D. Right? So this is the first important formula, that the nth term of such a sequence is A plus n minus 1D. Right. You're expected to know this thing by heart. What the nth term is, it's the first term plus your common difference times n minus 1. So I think we can close any entries now. We have advised these people to come in time, and it's disturbing us each time somebody comes. You can admit Fanuel, who calls himself the Great Fanuel. Right? You can admit him, but after that, close it, please. We don't want any further disturbance. So this is the nth term. This is the formula for the nth term. So this becomes a formula. Now, by the way, these sequences are called arithmetic sequences. So an arithmetic sequence is a sequence where you are adding the same number or subtracting the same number to get the next one. What you call a sequence which has got a common difference, right? Such sequences are called arithmetic sequences. Now, an important thing about this is that you can identify the nth term, but you can also add. There's a way of adding all the n terms. So if I want to add a and a plus d and a plus 2d plus a plus n minus 1, sorry, a plus n minus 1 times d, that's your last one. Let's call this L, L for the last term. Instead of this symbol here, it's a neater way of saying L for the last term. Okay, so now this is the sum of n terms, because there are n terms. This is T1, T1, T2, T3 up to n. So there are n terms altogether. Now the sum of n terms, I've got pluses in between here. Yeah, I was separating them by commas. I wasn't adding, right? But now I'm adding all of this. So what is this? There's a very nice formula for this. So this is called S with a subscript n. S standing for sum. It's a capital S, by the way. And with a subscript n, this means the sum of the first n terms of the sequence, sum of the n terms. Okay? And there's a very nice way of actually calculating this thing, because what we can do is, instead of adding all these numbers, we can add them backwards. So when you add them backwards, the same sum, I'll start with L, but the one before that, you have to subtract the D now to get the one just before that. Because I had to add D to this to get to that, right? So the one just before that is L minus D. The one before that one is L minus 2D, and so on until you come to the very first term, which is A. Right? So when you write it backwards, you'll end up at A. Now, there's an interesting thing that happens here. When you look at these two, I've got the same sum. So you got twice Sn. Now add like this. A plus L. I add these two. When I add these two, the D's cancel. And I got A plus L again. Here, the two D's cancel. And I got A plus L again. And so on, until the last one is also A plus L. Now, this is very nice because you got the same number added to itself n times, because there were n terms in the sequence. So what we have here is that twice the sum is actually equal to A plus L added to itself n times. And you get, and that's easy. So twice Sn is A plus L added to itself n times. So it's n times this. If 6 is added to itself 17 times, it's 17 times 6. So you got this formula here that Sn equals n over 2 into A plus L. So this is your second formula. If you look at this carefully, it's the same as saying the n, and if you put A plus L over 2, It's the same thing. So this is the average of the first term and the last term. See? So if you want to add up everything, you take the average of the first and the last term and multiply it by the number of terms. This is the number of terms. See? So these two formulae is all that we will do. There is another formula which I'm not going to bother about. But for our purposes, we need to know these two formulae. I've written the formulae down in wherever the problems are. So, but it'll be very nice to remember them. Okay, because I'm not going to make reference to this all the time. All right, so that's the background. So we are saying, to sum up, we are working with arithmetic sequences where the difference is common. And then you got a first term. So these are the symbols, the first term. And then you got the difference, the common difference. And the n represents the number of terms. Remember, the n is very important, the number of terms. And sometimes I use the symbol, the last term, for the very last one. And we know a formula for the last term. It's a plus n minus 1 times d. Right? So those are the symbols that we have. And then if you want to add up all the n terms, you take the average of the first and the last term and multiply it by the number of terms. Okay, so with that, I'm going to go straight into the problems. This is in your syllabus, by the way, so if you haven't done it yet, you'll certainly come across it in your school career. Okay, now not all the problems are like this, but I've just introduced those problems to you so that when we come across them, I can rely on the formulae. Okay, now let's look at the first question. There are 100 soldiers in a detachment. See, detachment is a term in an army with soldiers in a detachment. And every evening, 3 of them are on duty. So let me just put this to the three men are in duty in a guardhouse. So every evening. Now the question is, can it happen that after a certain period of time, some soldier, the 100 of them, has shared duty with every other soldier exactly once? So what is this? You are saying that some soldier, let's call this fellow, let's put a tick dot for him. Right, so maybe the first day he shares, he does a duty there. Right? So the first day. Second day, he shares with every other soldier. So he's there all the time. But now you got two new soldiers. Right? I'll still put this down like that. And the third day, you got two new soldiers. And the question is now, is it possible that he shares this with everybody like that? So what happens is really you've got, if you put it like this, that the first day you got two people. Second day, same guy, two people. Third day, same guy, two people, and so on. And eventually you say, is it possible that all 100 soldiers can be sorted out like this? Now, the answer is, it can't be. No, you can't have 100 soldiers because each time you got 2 plus 2 plus 2 plus 2. So the number of soldiers altogether at any given time is 2 plus 2 plus 2. Okay, somebody asked me a question. I'll come back to that person just now. So you got several twos, but there is also this guy here who is sharing with everybody else. Now, this is an even number plus 1. So this is an odd number. So you'll always have an odd number. So you can't have 100 soldiers doing this because 100 is even. See? All right, let me just see everybody here because somebody had a problem. I'm not sure how to deal with it. Let me just stop the share for a moment. Somebody has got a problem that the screen went blank. If that happened to you, can you just put your hands up? It seems to me that only one person had that problem. So that problem is located at that person's. Oh, okay. Clearsy raised a hand. Is anybody else? Okay. Oh, there are others. The screen went blank, huh? Okay, so there are quite a few people. It seems to me, okay, what I'm going to do is I'm going to leave now. And please, though, all of you, you can leave, exit. You see at the bottom of your screen, you'll see a leave, and then come back, join again. All right. So I think we have to rejoin. Perhaps it's been cut off from these people because, no, wait a minute. We don't have that problem with this group. I'm not sure. Khotso, can you help them? These people say that the screens went blank suddenly. Khotso, are you still there? Khotso? Okay, we have a number of people whose screens went blank. Okay, guys, I'm just going to call Khotso. I'm not sure why he's not here. He's supposed to be here.
Also, Prof, I went outside. I'm back.
Yeah, please. We have a problem. A number of people, their screens went blank. And I don't know what the reason.
Including mine.
Oh, yours as
yes,
well.
As well. Yes.
Do you know how to solve the problem?
Can you please refresh your screen maybe on your side?
On my side?
Yes, Prof.
How do you refresh? I don't know how to do these things. How do I refresh?
Let me check.
We're through the first question. And we are through with the first question. We now get on to the second one. The second one, all right, so the first few problems were involving these things about odd numbers and even numbers. And let me say a few things about that. We will come to these sequences later on. Okay, now there's some things which you know, but I'm going to just quickly record it. There's some general rules about odd numbers and even numbers, right? When you add even plus even gives you even. I think you all know that. Even plus odd is odd. 5 plus 6 is 11. That's odd. Odd plus odd is even. Right? 7 plus 5 is 12. Then you also have multiplication. Even times even is even. Now, this is an interesting one. Even times odd is always even. When you're multiplying, 12 times 7 is still even. Right? 4 times 7 is 28. The only time you have is odd times odd is odd. So normally when you're multiplying two numbers, it's mostly even. The only time it is odd is when both of them are odd. If one of them is even, the thing is even. So this question here says, which of the following numbers are even? Both m and n are both odd. So here you have odd times odd, right? So this is odd here. Here, both are odd. So you got odd, 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 because m squared is odd. And when you're adding an even number to that, it's still going to be odd, right? And here you got m and n are both odd. So m plus n is even. You got 1 plus an even number. So that's again odd. And here you got, now this is 2m. 2m means this is even because it's multiplying by 2, right? So this one here, you need to think about this. This is even plus, now n is odd. And 3 times the odd is odd. And then you're adding 5 to that. So you got odd plus odd, which is even. And that is even. So there you got even plus even. And this one here is an even plus an odd. So this is odd. All right, this is just give you a quick practice as to how odd numbers and even numbers work. You know most of these things, but I'm just recalling this for you. But because you got now you got symbols. So we know that m and n are both odd. So we have to think of it in symbols rather than special numbers. All right, so the next problem would be this one here. Question 3. Given two integers a and b, consider the number ab into a plus b. So you got ab into a plus b. All right. Now, can you determine whether it's even or odd? But we're not told. Now, we're not told whether A is odd or B is odd or anything. We are not told. We're not given that information. And the question is, can we decide on this number here without knowing anything else? Can you decide whether it's odd or even? Well, let's just look at this. If A or B is even, then AB is even. Doesn't matter if the other is odd. As long as one of them is even, AB is even. So now you have an even number times something else. So the product is even, because even number times anything is even. So if one of them is even, then the product is even. So now, so we have to take the case that if neither is even, which means that both are odd. If neither is even, it means that both are odd. In that case, you have A is odd, B is odd, so you have odd times odd here. But here, you have odd plus odd, and odd plus odd is even. So now this becomes even. So this is still even. So the product is still even. So the answer to this question is, it is that this product is always even, right? In all possible cases. That's interesting. Although you don't know whether A and B are even or odd, but you can conclude that this product is always even, because one of these factors is always even. As long as one of them is even, then the whole number is even. That is in a product. Okay, so that takes care of that problem. And we go on to question 4. A certain country has coins having values 1 cent, 3 cents, or 5 cents. Well, this country is certainly not South Africa. You got no more. You don't have any 5 cents anymore. Yeah, I noticed a couple of 10-cent coins, but the 20-cent coins have almost disappeared. Even the 50-cent coins, because things are not cheap anymore. Nobody sells things for 50 cents. All right, so they're getting them out of the market. So you got all odd now. You got 1, 3, and 5 cents, right? Can one make a change of a 25-cent coin? So you got 25. You got a 25-cent coin. Those coins don't exist anymore. And you're going to make a change using 10 coins. Right? Using 10 coins. Using in all 10 coins. 4, 5, 6, 7, 8, 9, 10. I think I've got 10 here. Right. Now, is it possible that you can get these 10 coins to eventually give you 25? So that's a question. Now, I know when I ask this question, sometimes I used to ask this question, people will try, you know, to see whether they can get 25 cents with 10 coins. But you don't have to do much because you see, all of these are odd. That's a nice thing. So if you take any two of these, this is going to be even. So if you take any two of these together, you're going to get an even, and you're going to get 5 even pairs. So you're going to get 5 numbers which are all even, and you can never get, when you add 5 even numbers, you're going to get even. And that can never be equal to 25. See? So when you got 10 coins like this, you'll always get an even sum because it's 5 pairs of odd coins. So it's 5 evens. So the answer to that question is no. They ask you, can one make a change? The answer is no. All right. So let's move on to the next question. So this is all about odd and even numbers. So we're having some practice about how to deal with these kinds of questions. So let's get on to the next one, which is that. All right, now you have, how many integers are larger than this? Oh, you got quite a big number here. It's 8 digits, 8 digits. So this number is a 16-digit number, presumably. And you got another 16-digit number, and you want this number to be, you want to know how many numbers are larger than this, but smaller than this. All right, so the way to do this is the following. You see, if you look at these numbers, although they all look quite frightening, here you got a square here, right? Let's give it a name. When you have these big numbers, you can tame this number by using a symbol. So this is really n squared. All right, so if this number is n, 2024, 2024. Now here, this number here is 2024, 2013. So this is really, if you add 11 to this, you'll get this. So in other words, this number here is n minus 11. It's 11 smaller than n. Now the same thing here, this is, you got 2035. To get to 2024, you have to subtract 11, right? So this is this number here plus 11. So now you can make this problem, you can translate this. So the question is how many integers are there larger than this? So you can say between n minus 11 into n plus 11. This is n minus 11 into n plus 11 and n squared. This is n squared. So this becomes a question. How many numbers are there between this number and this number? Now, this is a very well-known object here. Whenever you got a minus b into a plus b, I'm sure we've said this before, this is always a squared minus b squared. A very simple way of simplifying the product of the sum of two numbers and their difference. Right? So this is n squared minus 121 and n squared. So you want to know how many numbers there are between this. So you want it to be larger and smaller. So now, to make this larger, you have to add 1 to this. So we are looking at n squared minus 120. Right? That's the next one. The one after that, you add 1 to this, it's n squared minus 119. Right? Because you're adding 1, it becomes this. The next one is n squared minus 118. And you are going to stop when you come to n squared plus 1, because you want it to be it must be smaller than n squared. I'm sorry, n squared minus 1. And the next one will be n squared. But you are only going to count these numbers here, which are larger and smaller than n squared. So it's n squared minus 1, it stops there. Now, you can easily count them. You can see it's 1, 2, 3, up to 120. Right? So the answer is 120. You can count it. If you look from the backwards now, n squared minus 1, n squared minus 2, up to n squared minus 120. So you can see the 120 numbers in between. So that's the answer to that question. Now, at this stage here, I just want to pause a little bit to explain something. See, very often you have this question here. How many numbers are there? For instance, 18, 19, 20, all the way up to, say, 37. If you've got consecutive numbers, how many numbers are in this? Okay. The answer is, I've said this before, the answer is not 37 minus 18. You might think it's 37 minus 18, but that can't be, because if I ask you how many numbers are there from 18 to 19, it's not 1, it's 2. See? So you can subtract these, but you must add 1 to it. So 19 minus 18 is 1. You add 1 to it to give you the correct answer. So the number of ways, the number of numbers in a consecutive, if they are consecutive, one after the other, you take the last one, subtract the first one, and add 1 to it. See? So in that way, you could have done this. We could have taken n squared minus 121 And then we've got, they are consecutive numbers going all the way up to n squared. Right? So I could have said, these are all consecutive numbers. I could have said the number of numbers in this is, we know the answer is 120, is n squared minus the very first one, n squared. Yeah, oh, but wait a minute. You're not allowed to include the 121. You're starting with n squared minus 120, and you're landing up with n squared plus 1. So we are counting how many numbers are there in that set. So one has to be a little bit careful here. And so if I were to do this, then I will say, how many numbers in this? Well, here you can see this n squared minus 1. Yeah, it's quite easy to see. It's 100. But we'll come across other cases where you have to take this minus the first and add 1 to it. All right. Okay, let's get on to the next one because we're wasting time with these issues. I'm going to go into question 6. I write down all the consecutive integers from 25 to 208 inclusive. All right. So we can see we can write down all these numbers. And the question is, how many digits have I written down in total? So when you first start from 25, you've written 2 digits. Now you've written 4 digits, 25, 26. The 2 and 5 are the digits. Right. So you can go all the way up to 99. These are the 2-digit numbers. But then after that, you got 3-digit numbers. 100. So now you'll add 3. You can add 2 up to this point here. Right? But from this onwards, 101 all the way up to 208, here there are 3 digits each. While here there are 2 digits each. So the question is, how many digits do you write altogether? So that is why you have to stop at 99 because that's the last time where you put a 2-digit number. Then the count is different now. It starts counting 3s. Right. So you want to know how many digits are there altogether. Well, the way to do this is you want to know how many 2-digit numbers are there. And I just told you this, the number of, these are all consecutive numbers. So the number of digits. Now listen carefully. First, I need to know how many numbers there are. And we said it's 99 minus 25 plus 1. We said last one minus the first one, add 1 to it. That's the number of numbers. And each number produces 2 digits. So this is the number of digits in this lot. Now here, I have to multiply this by 3 now because each one has got 3 digits. But first, how many numbers are there altogether? It's 208 minus 100, last one minus the first one, plus 1. We said we must add 1. Oh, you can only do this for consecutive numbers. Be careful. So you can't do this in any situation. It's the last one minus the first one, add 1 to it. And this gives you the total number of digits in that lot. So you want to know what the total number of digits altogether is. You can just work this thing out, and I think you got 477. And I'm not going to waste my time showing you how you're going to get that. This is the way to do this. Count the number of 2-digit numbers multiplied by 2. Count the number of 3-digit numbers multiplied by 3 to get the total number of digits altogether. And the answer is 477, as I recall. Okay, let's now get on to the next question. Okay, now here you got the sum of 2025 consecutive integers. Now we're talking about sums. means now that we are going to what I told you earlier on. So you're adding consecutive numbers, right? And the question is, what is the largest integer in the sequence? Okay, they are consecutive integers. So let me write down the information. I don't know what the first one is. They are they didn't say it starts from 1. They just say consecutive. And there are 2025 of them. So it can start from anywhere. So let's call the starting point, we'll call it A, because earlier on, I told you when you go to sequence, the first term we normally write as A. They're consecutive numbers. So it's A plus 1 is the next one. A plus 2, right? And you've got the sum of 2025 of them. 2025 of them. So altogether, you got 2025. And you're adding all these things. Remember, first term, second term, and so on. And they say the sum is 2025. Okay. Now, you can see the first term is 1, and the common difference is D, which is 1. Because you're adding 1 all the time. Right? And we said that the last term, I got the formula down here. You might not be able to see it. It's written very, very humbly at the bottom here. Not sure that I can actually pick this thing up. But anyway, the last term, if you remember, we said was A plus N minus 1 times D. So the formula we had is, also don't allow that person in. So you got, the formula was Tn, or the last term, is A plus N minus 1 D. So the N here is, the number of terms is 2025. It says here, there are 25 consecutive integers. So your N is 2025. So the last term is A plus, you have to subtract 1, it's 2024. D, and D is 1. So 1 times 2024. So this is the last term. Okay, so when you add up all these things, you're going to get 2025. Right? Now we know a formula for the sum. If you know the first term and if you know the last term, I told you, you find the average of those two and you multiply it by the number of terms, and that will give you the sum of the n terms. Right? So here the sum of these terms here, we already know the sum is this. Right? It's equal to the number of terms, which is 2025, times the average of the first and the last. So it's A plus the last term we calculated is that. So it's the first term plus the last term, and the average of those two is you add those two and divide by 2. Right? This gives you the average of the first term and the last term, and you multiply that by 2025, and now we got only one equation of the one unknown, namely the starting point, the first number. Right. Now you can see the 2025 cancels. So you got 1 equals, and here you got A plus A, which is 2A, plus 2024 divided by 2. Right? And Okay, you can divide every one of them by 2. So you get A plus 1024. I'm sorry, 1012. So you divide this by 2. So you get 1 equals this. So therefore A will be equal to 1 minus 1012. That's your unknown, right? So you bring it to one side, A, and you take all the numbers and bring it to the other side. And 1 minus this is negative 1011. Okay, so the question is now, what is the largest integer in the sequence? And the largest integer will be that one, the last one. Because you're increasing, you got consecutive numbers, the largest one will be the last one. So the largest, that's the question, what is the largest integer? The largest is A plus 2024 and A is negative 1011. So this is equal to 2024. Let's put that in front, minus 1011. And that is 1013. So the answer to the question is 1013. The reason why I'm hesitating is that when I calculated this thing the last time, I got, I made it 2025. Okay, so I made this thing a 2025 question. All right, so it's 1013. That's the largest number. Okay, so I hope you understood that. So we use the formula here. First, we have to observe that it's an arithmetic sequence because you're adding the same number right throughout. Then, once you do that, then we can work out the last term. There's a formula, which is A plus n minus 1d. And once I calculate the last term, then I can calculate the sum, because the formula for the sum is n over 2, n times the average of the first and the last. That's what I did here. And then I see that I've only got one equation with one unknown, and that's A, and you can calculate that. Once you got A, you can calculate the last term. All right. So let's get on to the next one. And now I'm going to go a little bit faster. In the sequence 5, 11, 17, and so on, how many terms are less than 1,000? Now 5, 11, 17, in other words, you're adding 6 all the time. All right? So in other words, this is a common arithmetic sequence. The common difference is 6. But I have another way of doing this thing here. Because the common difference is 6, you can create multiples of 6 here. So I got 5, 11, 17. You're going all the way up to 1,000. Now suppose we want to know how many terms are here. So instead of counting how many terms are there, why don't I just add 1 to all of them? The reason being I can get multiples of 6. And that's easy to calculate. Because I've got 6, 12, 18, and I need to know all multiples of 6. So I need to know where I need to get numbers which are as close to 1000 as possible. So you need to know what is the last multiple of 6 before 1000. Okay, now if you look at 1000, the one before that is 999. It's not a multiple of 6. 998, this is can't be a multiple of 6 because the sum of that, it must be, for it to be a multiple of 6, it must be even, right? And it must be a multiple of 3. So I really have to leave that out. 998, 996. Now this is certainly a multiple of 3 because when you add them, you get 24 and it's even. So this is the last multiple of 6. It stops there. Because if you add one more to this, you're adding 6 each time, right? Okay, so if that is the case, the last number here would have been 995 because they are all one less. So this is where it goes up to. And you want to know how many numbers there are up to 995. See, if you add 6 to this, it's gone to greater than 1000. Right? So this is the last one. Now you can count the 6 times 1, 6 times 2, 6 times 3. So you need to know this is 6 times what? So you have to divide by 6. And when you work this thing out, you get 166. So therefore, this is 6 times 1, 6 times 2, 6 times 3. This is 6 times 166. So how many numbers are in this sequence? The answer is 166, right? Multiples of 6. You can do it like that. Or we can say this is the arithmetic sequence, and we need to know what the general term of this is. We want Tn, the nth term, to be less than 1000. The terms of the sequence, and you want to know the largest value of n. Right? N is the number of terms, you see. So you want to know what is the largest number of terms that you can have, which are less than 1000. Now we got a formula for this. This is a plus n minus 1 times d. Now, a is 5. We are looking at that sequence. It's 5. The n is unknown. And we know d is 6 because you're adding 6 all the time. So this is n minus 1 times 6. Let me put the 6 in front. Is less than 1000. So let me just move over to the other side to create some space here. I will draw a nice division line here. Right. I got 5 plus 6 into n minus 1 is less than 1000. So now we need to calculate the largest possible value for n. So you got 5 plus 6 into n minus 1 is less than 1000. Then you got 6 into n minus 1. I'm giving you another way of solving. I've already solved the problem, but I'm giving you another way where you can use the formula. So it's 1000 minus 5 is 995. So you have n minus 1, or if you like, you can say 6n minus 6. So it's 995 plus 6. I got minus 6 here. Take it to the other side. So you have 6n is less than 1001. And when you work out n is less than 1001 over 6. And here you got 166 and 5/6 when you calculate this. So you want the natural number, the largest natural number, counting number, because n is all a counting number, less than 166 and 5/6. And there you see the answer comes out, is 166. You want to know the largest natural number, which is smaller than this, and it's 166. Right, so that's another way of doing it, but I prefer this one here because you're not using any formulae or anything like that. You can just use it by using common sense. Right. Always try to use common sense in solving these problems. Okay, so the next problem is, again, we are doing the same things. Yeah? We are working with sequences. For each positive integer k, let sk, this is not nice. You can't use the symbol s. S is for the terms, because this is a sequence, not the sum. So let's just call this tk. Right. Let tk denote the increasing arithmetic sequence of integers whose first term is 1. Or maybe this sk is a sequence. Let's not worry about the terms. You got an arithmetic sequence of integers whose first term is 1, right? And whose common difference is k. So in other words, it's arithmetic sequence. I've told you what an arithmetic sequence is. It's a sequence where you keep adding the first number, and they tell you what you're adding. You're adding k. That's a common difference. So the next one will be 1 plus k. The next one will be 1 plus 2k. Because you keep adding k, that's a common difference. And we saw that this will be 1 plus the nth term. This is the nth term. Is that. Okay. So they give me an example. They say, for instance, if k is equal to 3, then you're going to have 1. 1 plus 3 is 4. And here you have 2k. If k is 3, 3 times 2 is 6. 1 plus 6 is 7. That means you're adding 3 all the time. If k is equal to 3, you're adding 3 to get that one. Now the question is, for how many values of k, now this is the tricky part, does the sequence, it's referring to the sequence, contain the term 2025? So you got a sequence here, we don't know what the k is, but amongst the terms, you got 2025. Amongst all these terms, you got 2025. Which values of k will force 2025 to be in the sequence? Like here now, you don't know if 2025 is in this sequence. Or if k is, for instance, 9, then you have 1 plus 9, which is 10. 10 plus 9 is 19. 19 plus 9 is 28. Maybe 2025 is in this sequence. So the question is, for how many values of k would 2025 be in that sequence? So it's quite a tricky question, right? So the actual question is, what are the values of k if 2025 is one of the terms in the sequence? So we're going to say is Tn. Right? These terms here are Tn. So you want this thing here to be one of these terms. So Tn equals 2025. And here right in the corner, if you can see, I got the formula for Tn, which we've already used. So Tn is a plus n minus 1d is 2025. Right? Now, what is a? A in the sequence is 1. I can see a is the first term. So if you substitute 1, you get 1 plus n minus 1. And d is common difference is k is equal to 2025. So let's take the 1 on this side, take it to the other side. So I have n minus 1 times k is equal to 2024. Because if you take the 1 to the other side, sign changes, and you get 2025 minus 1. At this stage, many people will get stuck and they wouldn't know what to do. Now here's something. What you've got on the left-hand side is a product of two numbers, and they are integers, right? Because n is an integer, it's a counting number. We are saying first term, second term, third term, and k is also an integer. So you got the product of two integers is 2024. That's very important, because then it means that k then has to be a factor. But they say for each positive integer k, so it must be a positive factor. So you need to know what are the factors of 2024. And how many, you really need to know how many factors are there for 2024. So the question now reduces to, the question is how many values of k? That's the question. So now we come down to the situation where we are saying, how many k's k is going to be a factor of 2024, and how many values of k? So the question now is how many factors, positive factors, does 2024 have? Now we've answered this question. In another session, we calculated the number of positive factors for a given number, right? If you went over that lesson, you will recall that what I did was I factorized the number. This is 4 multiplied by 506. This is 4 times 2 times 253. And this thing factorizes because 11 goes into this. It's not easy to see. You can get to 11. 2 plus 3 is 5, you see. So it's 11 times 23. So if you write it as powers, it's 2 cubed, because you got 8. 2 cubed multiplied by 11 multiplied by 23. And that is the factorization of 2024. And the question was, how many factors does 2024 have? And there's a formula for that. You have to write it as a product of prime numbers, or prime powers rather, as we have got here. All powers are prime numbers. 2, 11, and 23 are prime numbers. And the answer, how many factors? You add 1 to each exponent. The exponent is 11 to the 1, 23 to the 1, and multiply these things. So you got 4 times 2, which is 16. So there are 16 numbers, 16 values of k, right? So k is not equal to 16, please. It's how many k's have you got? So you can write down all the factors of this thing here, and you will see that there are 16 of them. See? One of the factors is, for instance, is 11. Right? So if k equals 11, for instance, then what you are saying is 1, and the common difference is 11. So you got 12, 23, keep adding 11. You can be assured that 2025 is sitting there amongst them, because for every possible factor, 2025 will be in the sequence. Right, so that's it requires a certain understanding as to what this question is all about, and I try to explain it to the best of my ability. So let's go on. Okay, now the next question is, the nth term in a certain sequence is calculated for multiplying together all these numbers. All right. Now I'm going to go a little bit fast now because I don't have too much of time. So you're multiplying all numbers of this type. So for instance, a k takes on all the integer values from 2 to n plus 1. So like for instance, the third term, n is 3 then, you must go right up to 2 to 3 plus 1 is 4. So you multiply, you take all k values, take on all the values from 2 to 4. That means 2, 3, 4. Those are the k values. So if k equals 2, you got that one. K equals 3, you got that one, 1 plus 1/3. K equals 4 is that one. So you stop there because you must go up to n plus 1. And then you multiply all these things together, as you see, right? And we can actually multiply all these different square roots together, and you can put them under one square root sign. And if you look at this 1 plus half, that's 3 over 2. 1 plus 1/3 is 4 over 3. And 1 plus a quarter is 5 over 4. So you got square root of 3 over 2 times 4 over 3. This gives you 4 over 3 plus 5 over 4. And that simplifies to 5 over 2. But watch, when you're simplifying, these 3's cancel and these 4's cancel. And so that's how you get square root of 5 over 2. All right. Now this is when you're talking about the third term. Right? But suppose now we don't, the third is not given. Okay, we don't admit this person, Kotso. All right, so now it doesn't stop at 3. So let me just write down what happens here. You got square root of 1 plus 1 over k. You can simplify this by putting common denominator k. You get k plus 1. So this is the square root of a fraction, a single fraction, where the numerator is 1 more than the denominator. I'm going to repeat this. This thing here is a square root of a fraction. The numerator is 1 less than the denominator. And that is how I had 3 over 2, 4 over 3, 5 over 4. Right? So what we are doing here is multiplying. We'll put them all under a single square root. So you're multiplying 3 over 2, starting from. I'm not going to put that in brackets. That's just. Three over 2. I'll put them all under. You got a product of several square roots. You can put the first one as 3 over 2. The next one is 4 over 3, as we saw. Next one is 5 over 4. But it goes on now until you come to the very last one. The very last product is square root of, it goes up to k, the last value for k is n plus 1. K takes on all the values from 2 to n plus 1. So k is n plus 1. So this thing here will be, if k is n plus 1, you'll end up with n plus 2 over n plus 1. Right? Because k is n plus 1, you see. The last value for k is n plus 1. So the product finishes off here. And now there's some question. I'm not going to look at the question. I'm going to simplify this monstrous thing here. Like what we saw was these cancel, these cancel. In fact, all these cancel. And the last one to cancel will be that one. The one cancel the numerator there. But this survives. It doesn't cancel with anything. right? So this is square root of n plus 2 over 2. Okay, it seems to me that somebody thought that this class is starting at 6:30 and they told me not to forget the link. Anyway, now this is your nth term. This is the term. Is the nth term. They say find the smallest value of n for which nth term is a perfect square. So this thing here is the nth term over 2 at least. Right? That 2 survives. Remember that 2, so all the other ones don't. So that one together with this, that's how we had 5 over 2 there. And so you want this to be a square number. You want it to be a square number. The smallest value for n for which the nth term is a perfect square. Now, a perfect square, what are the squares? It's 1 squared, 2 squared, 3 squared, and so on. Right? So you want this to be as small as possible. So it looks as if it has to be equal to 1. Now, so you can try that. You can say, suppose the answer is suppose square root of n plus 2 is equal to 1. It turns out that then n is equal to 0 when you calculated n. Right? And that's not allowed because n takes on the smallest value for n is 2. So you can't have n is equal to 0. So this is not the smallest square. Let's try 4. So this time you have square root of n plus 2 over 2 is 4. And let's try to calculate n in this case. Okay, square root of n plus 2 over 2 is 4. So to get rid of the square root sign, you have to square on both sides. If you square it, you get 4 squared. And the square root of some number is 4. That number must be 16. Right? So this is how you get 16 here. Or if you like, squaring on both sides. So now you can solve for n. N plus 2 is equal to 16 times 2, which is 32. So n is equal to 32 minus 2. Take it to the other side. So n is 30. So the answer to the problem is 30. This is the smallest value of n because this doesn't work. So this will have to be, it works. So this must be the smallest value of n. You calculate it and you see that n is 30. Okay, so let's get on to the next problem. Okay, now this is relatively easy, so I'm not going to do this one. You can try this on your own. Question 11. But I'm going to try this one here. Now, we go on into a new domain here. How many odd positive integers, the sum of whose digits is 4 and none of whose digits is 0, are prime? I'll read that again. How many odd positive integers? So you got an integer which is odd. So that's a starting point. Right? So it ends in an odd number. The sum of the digits is 4. Okay, now that is, but they don't tell you how many digits it's got. So you could have a 1-digit number, and the sum is 4. Or you could have a 2-digit number, the sum is 4. So there you could have a 2-digit number will have to be 1 plus 3 or 2 plus 2. Right? The sum of those two digits must be 4, or you could have a 3-digit number. The sum of 3 numbers is 4. So what can you have? You can have oh yes. So these 2-digit numbers are going to be 13. That's the sum of the 2-digit numbers. Or you could have 31, or you could have 22. Right? This is the only 1-digit number. And here, the 2-digit numbers, which sum up to 4, is that. What about the 3-digit numbers? The 3-digit numbers, which sum to 4, are you could have 1 in the front, and the other two add up to 3. So you could have 103, or you can have 130, or you can have the sum of the digits is 4. Right? And so they can add up to, instead of 0 plus 3, you could have had 1 plus 2, or you could add 1 to 1, and that's 4 as well. I think that's it. So you can have 1 plus 3, or 0 plus 3, or 2, yeah. Okay, so these are the only ones, 3-digit numbers add up to 4. And as far as the 4-digit numbers are concerned, there's only one which adds up to 4, like that. Okay, so the number of numbers whose the sum of the digits is 4, but they say none of the digits is 0. Oh God, so you can take this out. And they were not allowed. And they must be odd, so I can take that out. So we can knock off quite a few, right? So we've knocked off the odd ones, the even ones, and none of the digits are 0, but they are not prime. All right. So this number here is prime. So I'm allowed for that. Allowed to put that in. 3, 1 is also. Oh, no, wait a minute. I'm not allowed. They're not prime. So this must be taken out because it's a prime. That must be taken out. Oh, yeah. We also have 2, 1, 1. I could have had starting with 2. Right? You could have had that. Can't start with 3 because 3-digit numbers, you can't have 3, 0, 1. You're not allowed to put a 0. Right. Okay, so you must knock out all the primes. So but it turns out that this one here is a prime. It's a prime number. Now you have to check the thing out. It'll take you a bit of time to show that it's not factorized by anything. But this one is not prime. 11 times 11. And this also 11 goes into this. Right. So there are only 2 numbers which satisfy this condition. The question is how many odd positive integers, the sum of whose digits is 4, and none of whose digits is 0, are not prime. So you have to translate your question nicely, and then write down all the possibilities and start eliminating them. So this is a strategy. The only thing I can teach you is how to, give you a strategy to solve these problems. But I can't deal with every problem. It's impossible, right? So you can't really prepare for these competitions or anything like that. You just have to have a lot of experience, try as many problems as possible, so that in all different kind of situations, you know how to tackle them. You see, I've got just one more, and I'll just quickly take that. I don't know what this is. Okay, I'm just going to finish this thing off. Now, I'd like to do this because it's an interesting problem. I have a 3-digit number, ABA, with A and B different. And the 3-digit number is not divisible by 4. Okay? And the sum of the 3 digits is 15. So I've got a 3-digit number, say for instance 4, but it starts with A and ends with 3. So I could have had 4 ends with A. The sum of the digits is 15. 4 plus 4 is 8. I could have had that, right? And it's not divisible by 4. Now this is certainly not divisible by 4, because for it to be divisible by 4, the last 2 digits has to be divisible by 4, and 4 does not go into this. So this is one of those numbers. I just took a chance and made this number, and it turned out that this was one of the numbers. But the question is, we don't want an example. You want to know how many such numbers are there. How do you go around solving this problem in general? You have to get all the possible answers. Okay, so for a starting point, the sum of the digits, 2A plus B, that's the sum of the digits. 2 times 4 is 8 plus 7 is 15. Now this thing here is 15. Right. So it means that, but B is a digit, right? The value for B is a digit. You can have, the middle digit can be 0. Now, let's do it together. If B is 0, then I have 2A equals 15, and that's not possible, because then A is 7.5, and A has to be a positive digit. So B is not 0. I can try B equal to 1. Then you have A, in that case, is 2A equals 14, so A is equal to 7. So you can have these two. Or you can have B, if you put B equal to 2, then 15 minus 2 is 13, and that's 2A is not odd. So the idea is, that the important thing is that B has to be odd, you see. It can't be even, because 2A is even, so 15 minus B is even, so B will have to be odd. See? So if B is 3, then you got 3, and then you'll have A and B are 6, 3 and 6. 5, you have that. If you have 7, you have 1, because, I'm sorry, 4. And B is 9. 15 minus 9 is 6. So these are your A and B. So the numbers are ABA is equal to A is 7, B is at the top. So I can write down the whole lot. 717, 636, 555. They must add up to 15. Right? A is 4, ending with 4. 3 is 9, ending with 3. So these are the numbers which are candidates for these things. Now let's have a look at this thing again. They say it's not divisible by 4. Right? So now this guy here can be taken out, because 36 is 4 times 9. But none of the other numbers are divisible by 4. The 474 I had as an example earlier on, and we said that that was in, because this is not divisible by 4. So it looks as if there are 4 answers, but be very careful. They say that A and B are different. You must read your question nicely. So here, A and B are the same, right? So you have to knock this out as well. So the answer is that, and that. So there are 3 and numbers. The answer is 3. The answer is 3. Okay, now I've actually written down the, I'm going to show it to you so that your assignment question, I've actually written it down here. So here's your assignment question. Let me just talk about the assignment question a little bit. They say you got a dartboard. You can score 3, 7, or 9 with each dart, and you can see where the 7s are. The 9 is in the middle, right? The highest score, and the 4 7s are in the inner ring, and the 3 are in the outer ring. And Samira hits the dartboard with 3 darts. The score is the total sum of the 3 darts. Now, how many different scores are possible? Right? So you have to write down all the possible scores, but there are only 3 darts. So you have to write down all the possible ways of getting with 3 darts, right? So it's a nice question. It's not very difficult. You can try to see. The 3 darts can be anywhere. For instance, she can get 27. See? She hits it with only 3 darts. All right. So I'm not going to give you any more hints there. That is your assignment question for the day. Okay, guys, that brings us to the end of today's talk. I've gone 8 minutes extra, as I usually do. My apologies. I always tell you, if you want to leave, you can go. Right? Let me just see if there are any questions. Are there any questions? If you got a question, please put your hand up. We've got a number of questions in the chat group. Khotso, I'm just going to look at these questions. I think most of them are administrative. Sorry, sir, we can't enter anymore. What about screens?